All right. So let me thank first to the organizers for giving me this opportunity to come and speak about dark matter at colliders. But I thought that I will also take this opportunity to speak about some of the ideas that we recently have about multipartite dark matter models and their possible probes at the collider level. So, and okay, so let's start with possible dark matter scenarios. Now, basically, we had wonderful talks by Dishita, Shotto, Ranjan, Asim. So they have covered many different aspects of dark matter. I will stick to the possible cold dark matter frameworks, which people usually talk about. And if you look into the classification, it basically has broadly two types of genesis, one via thermal freeze out and via non-thermal freeze-in. And within this thermal freeze-out paradigm, there are broadly this weakly interacting massive particle paradigm and strongly interacting massive particle paradigm. And for freeze-in, it's broadly this film type of dark matter. And when you think of multipartite dark matter models, any combination of them is actually a possibility. Now, when you try to build a dark matter model in particle physics, the basic idea is to extend the standard model Lagrangian to have an interaction between the dark matter particles and standard model. And so this operator O SMDM basically provides that kind of interaction. And depending on the mass dimension of this operator, you have to suppress by some new physics scale lambda of appropriate dimension. Now, this operator usually often is factorized into an operator consisting of dark matter particles only and with the standard model particles. And this factorization basically assumes that the dark matter particles do not transform under the standard model symmetry and vice versa. So yeah, so this GSM essentially denotes the standard model symmetry, while GDM basically talks about whatever symmetry that you want to have for the dark sector particles. And the simplest example, this was just talked about by Shotto in a moment, in the last minute, that the simplest dark matter standard model interaction that one can have is this Higgs portal framework, where you have a scalar dark matter phi connecting to the H dagger H of standard model. And this is a renormalizable interaction. And there are two parameters, lambda and mass of dark matter, which you can constrain from relic density and direct such constraints. And yeah, once again, because the different aspects of this dark matters have already been discussed by all these guys. I would also like to take this opportunity to talk briefly about the features of multipartite dark matter models. If you have more dark matter than a single component one, then there are, of course, I mean, you have to think of coupled Boltzmann equations to determine their relic density contributions. There are features like the conversions between different dark matter components. Then there are modified freeze out, which are driven by their interactions. And they, of course, have modified direct search cross section because the relic density is constituted by these two different components in many different possibilities. And of course, it finally gives you a larger allowed parameter space. And we must also satisfy the relic density constraint by these different dark matter components to add up to this observed one. All right. So now let's come to the collider signal of dark matter. Based on this dark matter standard model interactions that one can have, the dark matters can be produced at the collider. And this is nicely summarized by this cartoon by Tim Tate. And there are essentially two large class of possibilities. One, when you have a dark sector which has heavier particles in it, then you can in principle produce, and that have also standard model charges, then you can produce them at collider, and they finally decay to dark matters along with some leptons or jets, and this gives rise to so-called multi-lepton or multi-jet signals. And one of the popular example is, of course, supersymmetry. And the other possibility is that if you do not have an extended dark sector, And if you only have the dark matter standard model interaction, then you can only produce the dark matters. And then you have to depend on an initial state radiation of whatever particle that you can think of. And this gives rise to the second class of signals, which are called mono-X signals. Now, importantly, the point is that these dark matter particles cannot be seen at the detector level, so they miss the detector. And now, depending and this gives rise to a class of variables that you can actually measure in context of a collider. Now, the first important variable that people often talk about is what is missing transverse momentum, or MET. And this is basically defined as follows, that if you have lepton, jets, and photons in the final states which are produced, then you basically vector sum the x component and y components of their momentum, square it and take a square root, and this will basically give you the transverse momentum associated with the invisible particles that you actually produce. Then there is another variable that you can actually coin, and this is what is called the missing energy. And this missing energy is basically defined by summing up all the energies of all the visible particles that you produced at collider, and you take a difference from the center of mass energy of the reaction. And that is basically quantifying the energy with which these invisible particles actually escape from the detector. And the third variable that people often talk about is what is called the missing mass. And this is defined as that m/square is essentially sum over I pi minus sum over f pf. These are all four momenta of initial state and final state particles, and you take a square of it. So this also, in a sense, classifies or parameterizes the missing mass of the particles that actually escapes the detector. And of course, as you can all imagine, that this missing transverse momentum can be a useful variable in context of LHC and also for the linear colliders or FCC machines. However, the missing mass and missing energy, these variables can only be defined in context of colliders where you have the knowledge of the center of mass energy of that reaction. Because otherwise you cannot define them, because here also you require the center of mass energy, here also you require the sum of I of pi of the initial state collisions. So these variables can only be defined in context of E plus E minus machines, say for example. And of course, there are disappearing charge track, displaced vertex signal. So these have all been talked in details by Nishita, so I will not touch upon those. I will end this slide with two comments. One is the fact that particularly this linear collider of FCC, basically if you have E plus E minus machines, then there are actually, you have beam polarization, and you also have this longitudinal degrees of freedom, which you do not have in context of LHC. So these machines have some advantages over LHC, and this I will actually show more elaborately as I go along. And also, due to larger number of variables which is accessible to you whenever your dark sector is have more particles than the dark matter itself, when you can rely on this multi-lepton multi-jet signals which are essentially produced via the cascade from these heavier sector particles decaying to the dark matter. This will also be this is also more advantageous to probe than these mono-X signatures, because mono-X signatures have only one observable, if you wish, which is this particle X, whatever that you actually radiate. Okay, all right. So let's proceed. Now, this is the slide that I'm copying from Nishita, and this is something that we already know, that we have essentially two major experiments going on. One is the direct search of dark matter, and the other is collider searches. And we have null results from both of them. And in all different channels that has already been searched for. And I would just like to add one small comment here that usually whenever you have a spin independent direct search of dark matter possible, then that actually has more sensitivity than the collider searches, simply because of the fact that there is a huge background particularly in context of LHC, that one has to actually face when you do collider searches. So the exclusion limits, if you wish, from the direct searches, spin independent direct searches, are much more severe than the ones that you actually obtain from LHC. Non-observation of any excess in these signals, either in the multi-lepton, multi-jet, or mono-X searches. All right. So I will give you one example of dark matter search strategies, or some of the broad conclusions that we can corroborate from some cold dark matter candidates like fermion dark matters, which actually connect to standard model via this when you just stabilize those dark matters under Z2 symmetry. And then you can write this dimension 5 operators. I mean, these are pretty standard. I mean, and then there are these dimension 6 operators, which you can also write, which you can all write. I mean, here I'm only segregating between the quark bilinears and lepton bilinears for a particular purpose, and that will be clear in a moment. And there is another thing that I must say, that when you do effective field theory to actually write the dark matter standard model interactions or operators, you in principle, unless you are guided by some new physics, you actually should consider all the operators together of having same dimension. So basically, if you are focusing on some particular interaction, like for example, we are interested in this leptophilic dark matter, where we assume that the dark matter has this connection to the standard model leptons, then you have to consider all these operators, which actually gives rise to the connection to the standard model lepton doublets. And out of these 4, there are 2 which actually, you know, I mean, chi can be both Dirac and Majorana, but for Majorana fermion, you can only write these operators like O6, L, and L1. That was our nomenclature. And this leptophilic dark matter has this advantage, because I just mentioned that these direct search constraints are very, very severe from the non-observation of dark matter in the spin independent channels. So therefore, if you I will give you the numbers in a moment, that if you have interactions to the standard model quarks, then there is a severe constraint coming from the direct search, and that basically makes all these operators almost inaccessible in context of colliders, because the limits, if you abide by from the direct search, makes this collider cross section very, very tiny. However, for leptophilic dark matters, as you can imagine, that this interaction to the direct search occurs via one loop, so there is a suppression, and this suppression allows you to actually make the spin independent direct search a little more milder, and therefore allow you a larger parameter space accessible to probe these dark matters in context of lepton colliders. Okay, so this is basically, these are the plots that I was talking about, that if you take all these operators together, you see this is the relic density versus direct search allowed parameter space in terms of this dark matter mass versus this new physics scale lambda. And so this line is essentially the relic density allowed parameter space. When you take this CQI equal to 1, that means it has interaction with the standard model quarks. And you see that this black part is essentially discarded by the non-observation of dark matter in direct search, and this puts a limit as large as 3.4 TeV on the dark matter mass. So therefore, this is very difficult to probe at LHC if you take this kind of operators. However, this becomes a little more milder when you take leptophilic operators, and that is what precisely we show, like this line essentially. So this is for the Dirac dark matter once again, and this is the constraint coming from the non-observation in direct search constraint, and this basically gives you a dark matter mass around 345 GeV with lambda of the order of 2780 or something. I mean, and this line is basically for the for the case, you know, and then you can actually pick and choose which operator that you want to work with. I mean, which many people do, although we believe that unless you are guided by some new physics, all the operators should be considered together. And of course, you Shatto has already mentioned a while back that if you have Majorana dark matter, then the spin independent direct search cross sections are very, very mild, and you can live with very light dark matter masses also, and these are accessible to this you can probe in the collider as well. This one, right? Yeah, that's an interesting question. This is for CQ equal to 1. I think there will be some quark channel. This is, I guess, 173 GeV, and this is the top quark pair channel opening up for the annihilation of the dark matter. Because that this looks like 173 GeV, and so yeah. No, this is basically for the dimension 6 operators, not the dimension 5 ones. I mean, if you take the dimension 5 operators, then these are redundant. I mean, there is no need to do any of this business, because first of all, those will connect to via the Higgs portal only. Yeah. So that's it. Yeah. For this one, yeah, this must be some, yeah, this is D quark. This is perhaps, you are absolutely right. This is, yeah, those channels opening up. Okay, so let me, so this is one of our papers, I mean, which I'm quoting the results from. And then you do this, for this kind of models, you only have to rely on this mono X signals. So for example, we simulated for monophoton signal, and these are the distributions of these 3 key variables that I just pointed out, like missing transverse momentum, missing energy, and missing mass distributions. So these are the standard model background that you have. And this colored lines are actually for different dark matter masses and etc. So basically, there is one important point that I would like to mention, that in context of these lepton colliders, the right choice of beam polarization also helps you enormously in basically elucidating, in eliciting your dark matter signal and suppressing the standard model background. These are some numbers which you may or may not be interested in. And then there are some cuts that we actually put, like 0 lepton, 0 jet veto, missing energy, missing transverse momentum, and missing mass cut, which are used to get the significance at 100 femtobarn inverse of a lepton collider machine, which we are operating at the center of mass energy of 1 TeV. All right, so now let me come to this topic of what can be a potential signal for a 2-component dark matter. For example, if you think of a multi-lepton channel. Now, the first interesting point is the following, that the peak of the missing energy distribution essentially depends on both the dark matter mass and the splitting with the corresponding heavier charge fermion, which you can produce at the first stage of collision. Now, what do I mean? So, for example, if you think of SUSY, I mean, you can think of producing the charge-inno pair, and which is eventually decaying to neutral dark matter. So, basically, the peak of the dark matter distribution will be a function of delta M very strictly. Like, for example, delta M equal to 10 GeV will give you a missing energy peak around this position, where if you enhance the splitting of the dark matter and the corresponding charge particle, then the peak actually shifts on this side. Okay. Whereas there is a dependence on dark matter mass also, but this doesn't shift the position of the peak, rather this shift the end point of the distribution. Okay. So based on this fact, we say that suppose you take a missing energy distribution of suppose 1 dark matter candidate, and then if you have another dark matter candidate with a different delta M and M combination, then there is a possibility that these two different missing energy distributions actually superpose on top of each other and provide you a kink in the or a double hump distribution in the d sigma d missing energy versus missing energy plane. Okay, and this is indeed what we see, that these are some sample points that I'm showing where we have two different combinations of dark matter mass and the splitting which are put together, and you see that there is this double hump behavior which is showing up in the missing energy distribution. So therefore, we propose that if we see a two peak distribution in the missing energy or missing transverse momentum, this can actually provide you an indication of seeing a two component dark matter signal. And we also comment that the missing energy actually works better than the missing transverse momentum. So this same feature that which I'm showing in terms of missing energy, that same feature can also be seen in terms of missing transverse momentum. But missing energy is better than missing transverse momentum simply because of the fact that in the missing energy, the dark matter mass also enters. Okay. So this is how does the background distribution? I will be coming just in the next slide. Okay. So this is the time that I'm left with. Yes. Okay. For your talk, then 5 minutes for questions. Okay. So I have 5 more minutes to finish my talk. Okay. All right. So that's terrible. I will just come to the distribution with the background. So let me come to this thing. So this is a real simulation with a specific dark matter, or rather two different dark matter components, where we have a fermionic dark matter like a singlet plus doublet, which has charge components, which is finally decaying to the dark matter with leptons, and similarly a inert doublet model, which also gives rise to the same kind of a signal. And this is the standard model background that are there. And as Shotto was rightly pointing out, that if you take the background distributions into consideration, then all your signal distributions look very meager. I mean, this is your signal distribution. So the two humps that we are proposing is almost submerged completely within the background. However, this is the beauty of these lepton machines, that if you tune your polarization, and if you choose a right polarized electron and left polarized positron, that actually reduces the W background. This is simple because standard model has this left polarized interactions. So this is one important point, but that doesn't completely do the job. There is another thing, that if you plot the lepton energy in this dilepton channel, then you also see that there is something more that you can do, and you can put a lepton energy card on the lepton, and you see that you can actually reduce this very large WW background into a quite insignificant one. And then this is actually the distribution which puts together the signal plus background distribution, and you see that this two hub behavior can be retained. So this is basically what I talked about. And then of course we have to talk about that how do you, I mean, just you cannot rely on visualization that there is a two hump distribution. How do you identify those two peaks, and how do you segregate those two peaks? That has to be somehow which one? This is a lepton energy card plot.
If you merge the signal and the background, because that is what you will see.
Yeah, exactly. That's what I'm plotting.
The double hump.
Yes. That I will show in the next slide. I mean, this is just my slide. I mean, where I am actually, so this distribution, this, if you wish, is a signal plus background distribution. Now, I mean, you can see that we require a large luminosity and all those blah. I will come to that in a moment. But what you have to do, that you basically have to do a Gaussian fitting, and then you have to basically say that how far is the second peak from the first one, how high is the second peak from the first one, and so on and so forth. All these things have to be quantified. And so therefore we basically coin, there are 4 conditions, like condition 1 is basically you take this first peak, you identify the first peak, you fit this distribution with a Gaussian, two component Gaussian like this one, and then you identify this first peak, and actually you go to n sigma left and n sigma right, and you basically measure the number of events within that n sigma on both sides, and you basically take a difference and divide it by the square root of delta n1. So basically, if there is a second peak which is lurking within the n sigma of the first peak, then there will be a significant fluctuation. And so the condition is, if this RC1 is greater than 2, that is larger than the 2 sigma, then the second then there is definitely a presence of second peak. Similarly, there is a condition 2 where you can say, well, you can actually see the number of events with these two peaks, etc., and compare them. Then there is this third condition where you basically so the second one is actually this one, that you go to this side and you go to, suppose, k sigma distance, and you have the single Gaussian which is falling like this, and instead what you have is this one. You take the difference between y3 and y3 prime and take the square root here, and if you say that this is larger than 2 sigma, then also this gives rise to this idea of there is a second peak. And then there is this fourth possibility also, which is the difference between y2 minus y2 minimum. So this is the second peak, this is the minimum between the two peaks, and this actually quantifies how high the second peak is compared to the minima where these two peaks actually merge. And this you can plot in terms of luminosity after doing a real simulation, where the dotted points are actually the simulated points and the lines are basically extrapolation of those this thing. Now, I must comment what happens at LHC. This is really tough because of several reasons, so which I do not have time to elaborate right now, but this work is in progress. And then I will quickly comment about the mono-X signals and finish. So for mono-X, this is very harder to do. First of all, seeing a double hump behavior requires you at least to have operators of these two types to actually this thing, which relies on this key variables like angular momentum conservation, rotational invariance, collinear divergence, and the operator structure, which all lead to the double hump behavior in monophoton. For example, we consider these operators for monophoton, and for mono Z, these are the operators which gives rise to this double hump behavior. Now, the important point, so this is the paper which came out yesterday, and however, here I cannot do the thing that I was doing for multi-lepton channel, because the signal plus background distribution I cannot really tame down. The T channel nu bar, with a X after W mediation via T channel is absolutely untunable. I mean, so therefore the signal plus background distribution can barely show the two peak behavior in the mono-X channel. So what do? We propose that we look into the beam-wise signal significance distribution, and this does a good job. And once again, we do the same exercise as I just mentioned, and you see this two peak behavior is retained. And some of these parameters are essentially those ratios which I just mentioned. And so this is also from that same paper. So I come to the summary, and I talked about the possibility of looking into DMA-EFT signal at LHC. It is difficult for several reasons, mainly from the point of view that if you take direct search constraints seriously, then the productions at LHC is very meager. For the two component dark sectors producing dark matter via cascade decay, you can see a double hump behavior in ME or MET spectra in both multi-lepton and in mono-X, but the two humps in mono-X is much more difficult to actually obtain. The separation between the peaks depends on both these variables, which are also related to the dark matter relic density. So satisfying dark matter relic density, abiding by the direct search cross section, and still seeing a signal, it's a bit contrived issue actually, but we have done that exercise. And because standard model background plays foul, so beam polarization and lepton energy cut for two lepton final state actually are quite handy. But for mono-X, this event doesn't help. So what you have to, we are proposing to look into this signal significance in a binwise manner. And these conditions that we have coined can help you in identifying how high is the second peak, how far the second peak is from the first one, and so on and so forth. And and this last statement is a little this thing that we require both help from the polarization as well as from the statistics. I think currently the proposal from ILC is that, I mean, doing both is a difficult job, but this kind of possibility relies on both these things. So thank you so much. I must thank Professor Jian Judice. So there was a paper with Rakhi and all, like counting dark matter particles in LHC events. So this was one of the initial initiations of looking into this kind of prospects. And I also must thank DSTA CRB, this grant, because of which I could have one postdoc at our place at IIT Guwahati, and she was actually from IISc, and this kind of collaborations were possible. So with this, I thank you very much for your patience and attention.
Subhaditya, for a very nice overview on dark matter at colliders. Rohini, would you like to ask your question now?
Yeah, Subhaditya, thank you for the talk. Very clear talk. I wanted to ask you actually one question and one comment. So I'll make my comment first.
Yeah.
Is that since you have emphasized very correctly that this dark matter effective theory formulation works only if your chi does not transform under the standard model, which means that this is something that is not going to, no limit of our favorite SM or NMSM or extra dimensional models where our particles do have standard model interactions. Those are not going to get to these models with some limit. So I just wanted to emphasize that, just in view that if people forget this, because the younger people in the audience may think that these exclusions mean that our, the usual dark matter favorite UV motivated dark matter candidates are also ruled out to those masses. But that's not the case. There is a different situation there. And I mean, what I meant here is that even if the heavier particles are too heavy and the dark matter particles are not produced in the decay chains, even then the standard model quantum numbers of the dark matter particle will give some fusion, some funnel annihilation processes and so on and so forth. So the constraints that you see for a heavy dark matter in any one of those models are different than the ones that one is getting in this.
Actually, can I add a comment, Rohini, if you don't
please
mind?
do.
So basically, my comment of these limits coming from the direct search was very specific, as you correctly pointed out, to those models where we cannot take help of, say, for example, co-annihilation, semi-annihilation effects. Because those processes help in supersymmetry or in extra dimensional cases, or even, models with Z3 symmetry. Where,
and they contribute also to the detection cross-section, to the annihilation processes, to get the right relic. So I just wanted to make this comment to focus, because as I said, your presentation was very clear and you were making this point, but I wanted to say that this point is really and truly only in the dark matter, and you have correctly emphasized it. I just wanted to bring it once again to the attention. And the second is more a question. Why doesn't polarization help you in the last case? I mean, in general, are you trying to, maybe I'm confusing, understanding incorrectly, but in general, if I had a single dark matter candidate, monophoton was always something that I could do, right? I mean,
of course you can.
That is the classic signature of dark matter at the E plus E minus machine. Now,
Of
why
course.
doesn't polarization not help me?
No, polarization does help you, but it is not good enough to kind of make
see.
what I mean actually, Rohini, is that my specific comment regarding this was that we were proposing signal plus background distribution to show this double hump nature. But in monophoton case, there is this T channel W mediation where E plus E minus go
Yes,
to
it's a
nu
nu
and
bar
this
gamma.
W actually emits one of the photons from this one. So this particular process, you can reduce to some extent, but this is still, in the previous case, like when we talked about the multi-lepton channels, you have the WW background, W plus W minus product.
No, I understand. I understood by that, but my question is something slightly different. When I have a single dark matter, right?
Yes.
Then indeed E plus E minus going to nu bar gamma, which is the
Yes.
famous counting experiment almost.
Absolutely.
Okay.
No, that is precisely, Rohini.
Now, if I do linearly polarized electrons, I do reduce the nu bar gamma, no?
Correct. And this is
So-
precisely what this table actually
Okay. So I
So
guess
this is a single dark matter candidate. You can go to a desired signal significance, of course, as you are saying. But when we are talking about the double hump distribution, in case of a two-component dark matter, then it becomes difficult.
So the
if
polarization reduction is not enough.
polarization reduction is not good enough.
I see.
Polarization reduction is not good enough.
This is
Although
what,
if you
0.8? This is 0.8 or
yeah. So although if you notice that not only the significance, but just the signal by background ratio, if you take a note of those two, those are good. But if you have to retain this double hump behavior with the signal plus background distribution for mono X, that you cannot.
Other question.
Okay.
Yeah. Okay.
Thank you.
Okay.
Thank you. Thank you.
Thank you. Thank you.
I have a simple question. On the slide that you have the EFT dark matter operators, I just wonder where I can find the full list.
Yeah.
This slide. Where can I find the full list of these?
Oh, where you can find full list. So actually, there are many references, but I will quote one of the references that recently I wrote with
basis like in Smith, the Warsaw basis or something like this.
Yeah, exactly. So we wrote a review with Jose Udka, and it is called Effective Theories with Dark Matter Connection. And we made a table where all these different operators are put together. So there are many other references, of course, but I am shameless to quote my own paper.
So I have one question regarding the EFT analysis in collider.
Correct.
So, I mean, I can understand for the direct searches is quite low energy process, so the EFT cutoff is fine. But for the collider point of view, I mean, whether
perfectly a great question. So this is why in the summary and conclusion, if you remember, Rusa, I made the first statement was that DMEFT is difficult to probe at LHC. And this is precisely because of the fact that we do not have access to the partonic center of mass energy in case of LHC. And what people usually do, that when you are trying to probe effective theories at collider, there is one variable called invariant mass distribution of the final state particles. That invariant mass distribution basically pertains to what is the energy of the particular collision, right? The final state invariant mass distribution. But for the trouble for the dark matter is basically that final state particles are invisible. Suppose if you take mono X, there is only one single visible particle which is actually coming out. So getting a reasonable understanding of what is the new physics scale, and so what we do, that we say that if your invariant mass distribution actually the peak of the invariant mass distribution is actually smaller than the new physics scale lambda that you assume to simulate these events, then your effective field theory limit is validated, because you are saying that bulk of the events are actually coming at a scale which is smaller than the new physics scale. But whenever This is other way. So this is the way also you do tune your new physics scale lambda, so that you can validate your effective theory. But for dark matter production, this is very difficult to do. And so that's why I comment that at LHC, it is very difficult to retain the effectiveness of the dark matter theories. Whereas for the lepton colliders, you have access to the center of mass energy. And the simple limit is square root of S has to be smaller than the capital number. That's the answer.
Actually, I had two small questions about your analysis of separating the two peaks, just to understand.
Yes.
So one is when you showed that separation procedure, you already have assumed polarized beams and removed the backgrounds, one thing. And,
Yes.
And second, just small question, don't need to go there. Secondly, your B was the background. Does the background have an X distribution, or background is constant in?
Sorry.
So you fitted to a function with some G1 and G2, no, two
Oh,
Gaussian background. That background is constant in X, or does it have a background distribution?
No. So that B is it's a basically polynomial. Oh my goodness, I have to go to the slide. Yeah, that B has nothing to do with the background. That's just a Gaussian fit that I'm saying A1 into e to the power blah, A2 into e to the power minus blah, where you have the positions of the peaks of the first one and the second one. But there is a plus B, and that B has nothing to do with the background, because I have already taken the background plus signal into account in this thing. Now it's only the fitting function. So B is a polynomial in terms of X, if you wish, whatever the variable is. So I really apologize, I mean, if that confuses others, but that polynomial fitting has nothing to do. But what is important to check that you, when you do the fitting, you check this chi-square part degrees of freedom to see that if that is not very large and all that. So those are the things. Yeah, well, B in principle, you can assume it to be constant, but we see for a certain examples, depends on how you know, how good you want to, I mean, the more number of parameters that you have for the fitting, the better it is. I mean, essentially. So B you can treat as a constant as well. I mean, in most of the fittings that we have done, excepting for a couple of benchmarks, B was treated as a constant.
Yeah. I have a question regarding your analysis that you were saying you have considered all the operators at a time, right?
Yeah. Well,
So now you have so many operators now,
Right.
So that definitely will dilute your analysis, right? How do you conclude? I mean,
there is, I mean, see, I mean, we do both so that we do not know, annoy people who favors one particular.
no, it's not about favor.
No, what I'm trying to say, the answer is the following, that we do analysis for, suppose we essentially have 4 different operators connecting to standard model leptons. Now we take at one go, I mean, there are different things that you do that you can do because you do not have any control over the.
I hope all the operators doesn't have similar sensitivity to the phase.
Precisely.
You can easily check at the beginning and then you can go ahead, right?
Can I go to the slide where I show this? This is precisely that answers your question. Soumitra, if you see that this is essentially 1, 1, 1, 1 means all the Wilson coefficients that are taken together, and each of the Wilson coefficient have entries like 1. Then you see all these entries like 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0. So all these different possibilities are taken. And as you can immediately understand that those operators, which if you just remove the completely vector-like interaction, like chi bar, gamma mu chi.
That means you are not taking all the time, you are not taking all the operators simultaneously.
I mean,
that's
well, when we are doing the benchmarking and doing the
let us continue this discussion over lunch.
Okay.
So
okay.
we'll stop
Thank
here
you.
and thank you very much once
Thank
again.
you.